good day. Today we continue our lecture on design of springs, and this is the lecture number 29. Now, you see that for the helical springs we have already learned about the stresses, about the deflections and nomenclatures, the other design parameters what are required to be determined for a total design of an helical spring. So, what we do today that we take up a small design problem on helical spring and we will solve that problem, so that we will have a good revisit to the all what we have learned in earlier lectures about the helical spring. Now, the problem is defined here. You can see that a helical spring has been taken, which is acted upon by a load of 300 Newton and 900 Newton respectively. That means, it is working under a variable load, and for which the spring deflection will be around 15 mm. And other situation is that for some design requirement, the spring outside diameter should not exceed 50 mm. As a matter of fact, it should be within 48 to 50 mm. So, with this particular design problem, let us start today's lecture to solve the problem. In general, when we start the problem, then first of all we have to think of what? We have to think of a spring material, we have to think of the spring dimensions, and the most important to start with is a spring index, because the spring index gives you the ratio between the coil diameter and the wear diameter. Now, as because we can have a variety of choice of the spring index, we have to start somewhere. Normally, the spring index can vary over a large length, say starting anything between 3 to 12 or so. However, normally it is a good practice if we start the design with somewhat around 6 or 7, but anyway it is not the final answer, but one can start approximately designing the spring with a spring index C of value 6, because you know, if the spring index is more, then what is happening, the curvature effects will be lesser, whereas if you are having the spring index to be in a lesser side, then the curvature effect will be higher. But at the same time, what will happen, the larger the diameter of the spring wear, then lesser will be the stress in the spring wear, and vice versa. However, to find a unique solution to a design problem, one has to resort to a trial and error method, which is normally unavoidable in all design problems. So, in this case, we start the problem with a design with C equals to, you can see C equals to 6, and so corresponding diameter we are considering to be wear diameter to be 7 mm. Now, what is the basis of choice of this particular C equals to 7 and D equals to 7 mm? Because you can see then the capital D will be coming out to be 42, and you add to that the wear diameter. So, that comes out to be 49, and so this comes very much within the limit. So, basis of choosing the wire diameter 7 comes from the fact that we have to restrict ourselves the outside coil diameter within a value of 48 to 50. So, with this we take up the C equals to 6 and D equals to 7. Now, you know this problem is a dynamic problem. I mean, it is the spring is acted upon by a variable load. So, there are two situations coming into picture. One is the average, the mean stress F m, and another is the stress amplitude F a. So, in this situation what you are doing, that F a comes out to be 600 Newton and this comes out to be 300 Newton after calculation. Now, we know the stress concentration, shear stress concentration K factor K s will be given as 1 over this particular 1 by 2 C, that is 12, 1.083, and K w is 4 into 6 minus 1, 4 into 6 minus 4 plus 0.61 by 6. So, it comes out to be 1.253. So, we get the value of mean shear stress, that is tau m, is 1.083. There is a, this will be 600, please note down. So, 8 into F into the capital D divided by pi d cube, the standard formula what we have learnt earlier. So, that gives you the value of 202.62 megapascal, and stress amplitude in the similar manner comes out to be something like 117.21 megapascal. Now, the question comes about the what will be the material of the spring and what should be the corresponding strength values. So, we have seen that in the Soderberg criteria we require the material strengths like tau yield point and tau endurance limit, and both of these can be derived from either from the database, from the design handbooks, or we can have the relationships what we have learned during the spring design. So, here we choose a material, that is I am just writing over here, we choose a material, let it be chrome vanadium. So, we choose a material chrome vanadium. So, if we choose the material as chrome vanadium, then immediately we know that the relationship for ultimate strength comes out to be 1790 by this d to the power 0.155. So, you please refer to the earlier material property lecture, and from where you get the formula and the indices value of A and this value of M. So, that gives you a value 1324, and again if you go back for the relationship of sigma ultimate to sigma yield point, then you will be finding out this yield point is sigma ultimate multiplied by 0.51 for chrome vanadium, and endurance limit is sigma ultimate multiplied by 0.2. So, if you get these are the two values what you get from this calculation. So, once you find out that material property, then what we can see that we substitute these values into the equation of what is this comes out to be. This you know, this comes out to be tau mean by tau yield point, tau stress amplitude by tau yield point, twice of tau yield point, this is 2 tau yield point, this value, and this is tau endurance. That gives you a value of factor of safety as 1. So, the design do not have any factor of safety, means it is just you are utilizing the material property and getting the answer for the spring dimensions. So, it is better that normally for any design of the springs we go for a factor of safety which should be more than 1 and in the vicinity of 1.253, maybe 1.5 or so, it will be better. So, that is the reason we take up the next iteration where we consider the C equals to 5 and D equals to 8 mm. This choice is obvious because C 7 and D 6 will be giving us the more stress on the wire, thereby the factor of safety will again decrease. So, let us go for the higher one, and just by following the similar procedure as above, we find that this is Ks is 1.1, Kw is 1.311 and we multiply the mean stress by Ks and the stress amplitude by K wall correction factor that we have already learned earlier, and this gives values of this nature. And in the same way, with using the chrome vanadium steel, we get for this case a tau yield point and tau endurance value is something like this. So, if we put this to the formula, then what we get? We get this values as, yes, these values we get as 0.6081 upon Fs. So, factor of safety comes out to be about 1.46. So, it is very near to 1.5 and this factor of safety is quite suitable for the design, and we accept the value of C to be 5 and D to be 8 mm. Okay. So, what we get, the capital D comes out to be 40 and outer diameter comes out to be 48. So, obviously, this is well within the limit prescribed and we can select these dimensions. So, once we select these dimensions, then we find out from the standard results, the standard formula what we have learned earlier, that D 0 comes out to be 48, D I 32 mm. So, what is this particular spring stiffness K or this spring rate, spring constant, whatever you may call it. So, 900 minus 300 by 15, that was a displacement for the load of 900 to 300. So, we get the value of K as this much. So, in terms of Newton meter, we get it this way. So, basically what you are getting is the slope something like this. If it is 300, if it is 900, we get an 15. So, that is a slope, this is the 15 mm is your displacement. So, force displacement curve from where we get the value of steepness. So, once we know the value of steepness, then what we can find? We can find out the value of number of turns. Value of number of turns can be obtained from this relationship. So, number of turns comes out to be 16. Then we come back to the idea that once we find out this number of turns, so this number of turns will be what we call as number of we go back to the earlier slide. Okay. So, this comes out to be the case this one, this 16 is number of active turns. So, once we get the number of active turns, then we have found out the maximum delta. This is the deflection of the spring, that comes out to be 22.5. Please note that we have assumed 80 into 10 to the power 3 this AMPA as the value of G. This is nothing but the value of G for the steel material can be assumed. Now, here you understand the load is 900 because because the spring was somewhere in between, squeezed from 300 to 900. This is 300, this is 900, it was squeezed in between. So, if you leave it, then if you leave it something is like that, then you put the entire 900, then this comes out to be your delta max. So, it is under 900 what is happening. So, that delta max we are computing to be 22.5. So, once we get this delta max, then what we get? We can find out for a square and ground end coil, that is an assumption. So, just one second, it should be squared and ground ends. So, for this type of spring you have seen earlier, this is the spring, it is flattened and grounded at the top and the bottom also. So, for this type of spring what we get, that we get the value of free length. This is a solid length. While going the solid length, if you just go through for the square and ground end chart, you will be finding out this is the total number of coil 18, that means 16 plus 2 into 8 is dia. This is the delta max, and we have assumed certain 15% of the total one to consider as an clash allowance, and that gives us approximately a value of 170 mm. So, once you know the free length to be 170 mm, then pitch comes out to be from this formula as 9.625. Now, we come down to the check for the buckling. So, we have seen that the check for the buckling is 2.57. This is the limiting value. 40 is the capital D divided by the end condition. In this case, the end condition comes out to be over the plates, and so it is 0.5, and that comes out to be around 206. So, I urge upon you to just look to the formula we have derived earlier, from where you find that this value is coming out 206 mm, whereas the value of the free length of the spring is 170 mm. So, obviously, there should not be any buckling. So, we go back to the case that what should be the frequency behavior, means what is the critical frequency of the spring, so that the spring do not have any surging tendency. Now, in this case we know the weight of the spring should be first computed to find out the formula of the frequency, and that formula you remember it was half as over here. I think I can just tell over here, this is the spring rate K, this is G, and this one is your W, the weight of the spring, total weight of the spring. So, you can see we have found out 2.47, then this is d square. So, that is a d square of pi by cross sectional area, pi by 4 d square, and this comes out to be pi dn, the total one. So, this mean dia of the coil, then the total number of active turns, and this comes out to be your this is your density kg per meter cube, and this is just to make in unit of meter per second square. So, this is a g value. So, kg meter per second square will give you the Newton. So, that is the thing. So, once you get these values, as the weight comes out to be around Newton, meter cube kg per meter cube, meter per second square. So, meter cube is meter square into meter cube. So, the unit comes out to be 7.74 Newton. So, this one thing you should be very careful about these units. Okay. So, while dealing with these SI units, you know the force should come out to be the weight, means it should be a force unit. So, that is Newton. So, once you put these values, it comes out to be 112.6 hertz, and that means what? That this is the frequency. So, we understand the safe frequency for design should be at least 20 times less than this frequency. Okay. Because if you take up 20 times less, then what happens, that not only the first mode, all of the harmonics for the frequency, I mean up to say around 20 harmonics you can take care of. Okay. So, that comes out to be approximately 6 hertz. So, the spring is safe times less, then what happens, that not only the first mode, all of the harmonics for the frequency, I mean up to say around 20 harmonics you can take care of. Okay. So, that comes out to be approximately 6 hertz. So, the spring is safe, that means spring frequency for design. So, that means while you are applying in actual application, it should be around 6 hertz. So, that gives you the total design of a helical spring. So, I hope that you understand that by this particular problem, what we have done, we have taken more or less all the aspects that what we have learned in helical springs, starting from the stress equation, the correction factors, wall correction factor and shear stress factors, the material choice, material strength choice, then the choice of spring index, and then you have seen that we have used the Soderberg criteria, that means variable load design. Then you have checked for the buckling, you have checked for the frequency, that is the surging of the spring. So, more or less we have seen that all the situations what we have learned has been taken care of by this particular problem. So, ultimately the values what we have computed right now in different stages are the typical spring design parameters for the given problem. Now, we go back to the another aspect, that is what we call as the leaf springs. So, after we have learned about the helical springs, let us come and concentrate our idea that how we take up the design procedure for the leaf springs. Now, basically if you consider a leaf spring, it is nothing but simply, if you take a spring material and just put a load over there, and then what will happen, it will just deflect, and if you just take away the load, then it will just go back to its original position, something like that. Now, in the sports you have seen the diving situations, that when the swimmers they dive from the diving boards down onto the swimming pool, you have seen the diving board just have a oscillations like that. That is simply a springing action. So, that is basically a leaf spring. So, this leaf spring, when we put it into a form, in some form, and that particularly when you see in the rear wheels and the front wheels of the automobiles, means mostly the buses and trucks, then those are the leaf springs what we actually design. But the fundamental principle lies over the fact that simply a steel material, if you just put a load, it deflects, and if you remove the load, then it goes back to its original position. It is as simple as it is. So, considering the fact that what I have just told you, let us look at the board. You can see this is a simple situation of a leaf spring, that what I has called a diving board. A swimmer is standing over here and he or she is going to jump. Well, here there is no question of jumping, the load is continuously falling over here. So, from our fundamental ideas, I mean the basic courses, we know that in this case the stresses will be bending stress is what you know, it is sigma equals to m y by I. So, if we put these values, then we get a stress value of this one. Please note that in this case, if I extend it is an 3-dimensional somewhat this thing. Now, this is your B and this is your H. Okay. So, this is the B, what you can see. If you look from the top, then this is the width portion B, sorry, this is the B and this is the H. So, correspondingly, if you are having, then moment of inertia I comes out to be B H cube by 12. So, this we are utilizing. So, once you utilize this concept, then all equations are clear to you. Similarly, if you have the delta max, means the deflection, where the deflection will be maximum, obviously the tip the deflection will be maximum, and this deflection is again given by this expression. Now, in the second case, you can see that instead of using a cross section having same cross section, we are taking a triangular sort of situation. Then the beauty of this particular type of triangular section, what is being shown here is that we call this is an uniform strength. See, this is very easy. That means, if you are putting on load F equals to here, somewhere at the mid section, what do you expect? That the bending moment will be FL by 2 and area will be, what is this one? This width will be B by 2. So, BH cube means B by 2 and other H cube will come into picture. So, immediately you can see the stress what has been calculated sigma max equals to this much will be the same what it is at this location, whatever at this location, but that is not the case over here. So, if we have a shape like this, then what is happening, that you are having that stresses at any locations will be the same, and that is what we call as an uniform strength, leaf of an uniform strength. However, in this particular case, what is happening, that this particular one, once you just look at the board, although the strength is what we call as an uniform strength cross section, but only thing is that the maximum delta is obviously larger than what we have obtained in the case 1. Now, if it is larger, then this gives one additional advantage, you know, from this particular design point of view. What is this advantage? That always you will be having a more resilience. Okay, the resilience of the spring will be more. You know, the resilience we have learned in our earlier course, it is that energy stored energy per unit volume, that amount of energy stored per unit volume. So, it will be having more resilience because it is having a more deflection. At the same time, what is happening, that is the material requirement for this uniform strength beam is much less compared to what we get for an beam of an uniform cross section. So, non-uniform cross section and gives you an uniform strength and lesser material and more resilience. So, this is in one way it is better design than in comparison to what we get for an uniform width beams. So, in leaf spring design, people normally choose this type of uniform strength situations. So, these situations are normally taken up. Now, if you take the second case, then in the similar manner we consider a simply supported beam for which these are the stress and deflection equation. In the same way, the simply supported beam, as if this is a central zone fixed up and two cantilevers working. So, in that particular case, you are having a stress of this nature and delta max of this nature, and this shape, this type of diamond shape, it is called a lozenge shape. The idea is the same. Now, what is the design theme? Just look into this slide that you can see, and the design theme is something like this. For the sake of explanation, just a case 2 of what we just learned earlier has been chosen, but anything, any one case you can take either for a cantilever or a simply supported. Here we have taken up a case what we just learned earlier. Now, just solve for the h, solve for the h, divide this equation by these equations, and I mean then what is sigma max by this one, it comes out to be what, that this design equation, if you just eliminate h out of these two equations, so h comes out to be sigma max E delta max into L square. Now, this sigma max you replace by a sigma design, that what we do normally in the design. Okay? The material, the sigma max what is coming out to be, will be the maximum amount of stress what we can expect in the design. So, in the design what should be the delta max, you to design, you to consider E is the material property and the value should be chosen for the type of steel spring material you are going to use, and the length is the characteristics length of the spring is also under your choice. So, once you have these values, this particular design parameters are known to you, then you find the value of h. Once you get the value of h, substitute back in this equation, then what you get, suppose in this equation if you substitute back, you get the value of b. Well, now here I think one should use the, instead of max, it is better you use the design. Okay, sigma design, the same thing what you have used. So, b equals to 3FL sigma design by h square. So, that gives you the value of h and value of b. So, for a given load and given length of the spring, you know what should be the leaf thickness and leaf width, that is all. So, this is the simple way of thinking a design for the leaf spring. So, once we find out the value of h and b, then one has to think in this line. See the b value what you obtained considering this aspect, that means you got something like this. Then this b with values of sigma, deflection and L, this is the b what you have obtained can be too larger dimension. Okay? It can be a too larger dimension to accommodate in a machine assembly. So, in that case a requirement comes into picture, and that is what we will be just looking in the next slide. So, this is what is the concept of the laminated springs. What you can see that just in the earlier slide we have seen that we could design what you can see that we have just designed this value of b. What I was telling is too big to accommodate in certain cases. So, what we will be doing is that instead of going for this large width, one can resort to a tricky way, that you make out make the stripes like this. Okay, this is one strip. Now, once you have taken it out, then this one, this 2 and 2 makes another one, 3 and 3 makes another one, and this 4 and 4 makes another one. Put one after other, one below other. So, this is basically 1, then this it is coming out to be 2, then this comes out to be 3, and this comes out to be 4. And if you have cut it like that, then this is the 1, this is the 2, this is the 3, and this is the 4. So, you view from the top. I have only drawn one side. Okay, this one side of this one is being drawn, that is 1, 2, 3, 4. So, what is the idea? You can see the width of each section B n is basically B divided by n. In this particular case, n comes out to be around 4, and you do not have any changes in the equations except for the fact that this B in the earlier equation is just changed in this fashion, and this is the case of P Q, the constants. This is for the simple beam, simply supported beam. This P and Q comes out to be 3 3. For cantilever beam, this comes out to be 6 and 6. So, this is the basic equation remains same if except for the fact that this n B n merely replaces the width B. An advantage? The advantage is that instead of this large width of the B, it reduces to a width of this particular situation, where everything remains the same. However, ideally what happens, just please look into the board once again, that ideally we do not have this type of very sharp edges, because you can see that whenever the load comes over here, if it is so sharp, then it won't have any load bearing capacity. So, normally what is happening that you can think of little bit of blunting of these sides, okay, something like this you can have, or simply you can keep the edges straight cut pieces. Well, for such modifications, what happens? Suppose this modification is being done over this one, then normally what happens, the stress equations do not change much, but the change comes into the certain aspects of the deflections, okay, because you are changing some amount of, I mean, basic shape you are changing from what you got the shape for the case of uniform strength. So, pure triangle is not getting a pure triangle, but it is having an truncations at the tips. But anyway, by such modifications you do not lose much, but you lose you gain in the terms of the strengths and other things for the particular lip springs. So, this is what we call as a laminated spring, that means these are all the laminations that what you are providing. So, now I think that you have seen such kind of springs being put under the automobile wheels, and where you can see that these are normally it will be clamped and the wheel will be somewhere here, and this particular one will be carrying the wheel, and these are the attachments. Okay. So, we will come down to those situations. This type of springs also you will be seeing below the the wagon, the railway wagon wagons which is carrying the loads, you will be finding out these type of lip springs are sometimes put in the wagon. However, normally nowadays more and more automobiles and other things are going for helical springs, because these lip springs are normally not very well suited for fatigue considerations. Okay. This is what I was trying to talk about, the laminated spring. So, this laminated spring has got this is the main line, So, this is what we call the top one as the master leaf. So, this is the eye for attaching with the automobile bodies or something like this. The amount of bend that is being given is called a camber, and these are the central clamp, and here the bolts are also there bolted to this one. This is called central bolt, and these are all graduated leaves what we are getting these things. Now, these are called rebound clips. Now, what is this rebound clips? The rebound clip is mostly required that whenever certain amount of loading coming over from here comes over the spring, this rebound clip helps to shear some loads from the master leaf to this graduated leaf. And this particular one is a central clamp, and this central clamp has got a central bolt to fix up. So, that has got some tendency to weaken up the springs, but anyway, as because the clamp has having some width over here, that takes off the total weakening effect by this particular clamps. And another thing is that this camber, what is this camber is being provided? See what is happening, that this camber is provided in one sense that whenever the load comes, that under the action of maximum, this is called a positive camber, under the action of the maximum load, when this spring deflects, at the most it can take off a straight portion. Sometimes if it goes in the other way, then we call that will be a negative camber, but normally this happens very rarely, and designs are made that this particular one, the camber is such that at the most it goes like this. Now, this is what we call the span of the laminated spring. So, this is called a laminated semi elliptic spring, and this is the one what you see in automobiles. So, we know this is the master leaf, rebound clip, the reason of rebound clip to shear the loads, then the graduated leaves, and central clamp eye. Okay. Now, actually this laminated semi elliptic spring do have the following materials. One is a plain carbon steel, chrome vanadium steel, chromium nickel molybdenum spring, silicon manganese spring. So, these are the typical materials what are being used for design in the leaf springs, and standard sizes of the leaf spring are given over here. The width is 25 to 80 mm. I think it one should write mm in steps of 5 mm. Thickness 2 to 8 mm in steps of 1 mm, and 10 to 16 mm, please note down this is mm, in steps of 2 mm. So, these are the standard sizes of a leaf spring. And next we would like to discuss something about the actual practice. What is the actual practice is this, that we have seen that this particular shape of the leaf is being cut into this one, isn't it, and that is put into the as a lamination. So, the top one, which is the middle one, we call as the master leaf, but normally what we know is that few more additional full length leaves below the master leaf for heavy loads. In actual practice, there is not only one master leaf, we may be having one or two more full length leaves placed below the master leaf, as we have seen in the actual lozenge shape plates. So, it is a deviation. So, actual design should have only one master leaf as per the simplification, I mean as per the design procedure, but in reality to take up more heavy loads, we do have more full length leaves. Now, what it happens that for that matter the value of stress do not change. Please note that the value of stress do not change, but what happens that just by virtue, just by putting some additional full length leaves, what you get is that the deflection equation changes, it requires certain amount of correction. Why? You understand, because the stiffness is changing, the stiffness of the spring is changing. So, in general you can consider that this deflection is somewhat 10 to 15% less than what is given by the basic equation. But one can also compute by a formula that what should be the actual deflection by putting some additional full length leaves under the master leaf. So, let us see what is that expression for. Since the expression of delta max is this idea is this is the delta max, you know the q value, it will be 6 or 3 depending upon whether it is in cantilever beam or this particular one is the simple beam. However, normally this laminated springs what we are designing is something thought of a double cantilever centered at the middle. Anyway, our idea was to find out what what should be the correction by putting the full length leaves below the master leaf. So, the correction comes out to be this one, this delta C given by this particular formula 1 minus 4 m 2 m square into 1.5 minus ln means log to the base e and m and 1 minus m cube, where m is a ratio given by number of full leaves to total number of full length leaves by the total number of leaves what you are using in the spring. So, this equation may be utilized for finding out the correction in deflection coming or arising due to the fact that you are having some full length leaves below the master leaf. Now, if we look to another aspect, that the stresses due to support hinges, as you have seen that all the laminated leaves are connected at the eye to the support. So, from the support some longitudinal forces do come into picture onto this leaf springs, and there is a possibility of stresses arising due to twists. So, what is the disadvantage? So, the disadvantage for such additional longitudinal forces and the twisting effect, that just what I have told you, is that the master leaf actually gets more and more stressed compared to what you are having for the graduated leaves. So, one has to find out some ways so that the stresses in the master leaves are reduced. Okay? That means, the master leaf stresses should be reduced compared to other stresses arising due to what? Due to the effect, one as a longitudinal force, another a possible twist. What are the methods to reduce these additional stresses? The methods are something like this. The master leaf is made of stronger material than the other leaves. Okay? This is one way. That means, if you make of a stronger material, then obviously the stresses it will be able to take up more. Another way is that you make the master leaf thinner. That means, the master leaf is made thinner than the other leaves that you are considering. So, if you make it thin, then obviously what is happening, that the stresses will reduce at the extremes, because your y is changing, y is reducing. But anyway, that is also not a, that is also one possible way, but what people do is the other one. The radius of curvature of the master leaf is larger than the next leaf. What this means, what this idea means, for which let us go to the next slide. See, this is a figure. What has been mentioned over here is just hold on, I am just coming down to the this idea. So, here we come. Now, as I was telling you that this is the master leaf and this is the leaf just beneath the master leaf. So, what you will do? You give this master leaf an initial bend. Okay. First of all, you can see the largest radius of curvature. This is having a larger radius of curvature compared to this one. So, obviously, there exists a gap between this master leaf and the next leaf. And what you apply an initial bend during assembly. How you apply the initial bend during the assembly? Just by putting the central bolt. If you tighten the central bolt, then gradually the master leaf will bend inward, and just have a look at the board. The master leaf will bend inward if you are having a gradually tightening in this way, and this will be coming closer to this one. So, what you are having is that the master leaf had a curvature of this nature, and you are making it more bent. You are making it more bent. That means, what you are doing is that you are incorporating a more stress onto this one. You got the point. So, this was this particular one. If you are having a bend, then what it will create? How you are applying the bend? As I told you, just by putting the clamp over here. Just you tighten the bolt from the both side, it will come closer and closer, and so that is what you get. Now, if you are bending it by this amount, then what is happening? That this is getting stress, means it is having a more compressive strength negative, and this is having more tensile strength. And what is happening to this one? This one was like this, it was having some stresses, and this particular one is trying to flatten out more. That means it will have a tendency of a, this particular one will having a tendency of a what, opening out stress. That means it is going to more stressed in these directions. Well, I will come down to this particular part later on. So, once you get a bend shape like this, it is creating some amount of initial stress onto it. Now, you look into a situation. Once you, in actual practice, once you give an heavy load over that one, then this bend shape will be trying to put a some sort of shape like that, means because it will be getting pushed like that. So, it is gradually going towards the tension side, and it was actually a negative. So, it has to overcome the negative and go to the positive side of stress. So, that means what is happening? Due to the loading, it will first relieve the stress and then get stressed. And in this situation, what is happening? That this particular one, what you are having, just by pulling it inside, I am talking about the next leaf, this is the next leaf, okay. NL I am just writing next leaf, this is the master leaf, this is ML and this is NL. So, next leaf is what is, I mean, it is already got a pull like that. So, when a load is coming over, then it is getting again an additional load like that. So, what is happening? If it were some stress, say if it is going like that, some stress will be what is happening, that it is going towards this plus. So, if it is going more towards plus, then the stress is getting added up. Okay. So, in this case the next leaves will be more stressed, but the master leaves gets a stress relief just by application of the load. So, this is what we consider as the nipping of leaf spring. As a matter of fact, what happens, you know, that not only the leaf spring, I mean next leaf, all the in between the leaves of the automobile springs, that means if we consider over here, then all the leaves will be having certain amount of this nipping. So, that certain amount of knitting, so that what you are having, that there is certain amount of gaps, all will be stresses will be uniformly distributed, and certain amount of dot accumulation in between the leaves also can be cleared. So, this gives the total design consideration for the leaf spring. So, very quickly if we just have a revisit to the leaf spring, then what we get, that first of all the design is a simple leaf. Just look at the board, simple leaf spring coming over here, you get the equations. Design theme is you divide this by this, get the value of H and the value of B, you laminate the width, put into the laminated form, and then this is the actual elliptic spring. So, the materials of the spring, you know, the standard widths are given over here, and in actual practice what we do has been told, and the lastly that a nipping of leaf spring is required. So, this ends our lecture on design of springs. Thank you.